go ahead and complete the experiments for the lever. These experiments are simulations in which we use CAD created devices to make measurements, and then for the data that's given to you in the form of a data graph. So this is in a companion number 2 to part 1, first class lever examples of activity 1.1 levers. Okay, so in this assignment you will be finishing investigating first, second, and third class levers at this link. So this is the MYPLTW link that takes you into this part right here, part 1. We'll be finishing part 1, part 2, and part 3, because part 2, if you go way down here, is second class levers, and part 3 is third class levers. If you go all the way to the bottom, you're going to see that we're all the way up to 64. And so this is quite long. And as you'll recall, this video here deals with just going with the first class lever.
Use this tape measure here on shape. I'm going to demonstrate.
This is my assistant, or friend, Percy, did this video, and it kind of leads you through 1 through 11, those steps. So the rest of the steps you're going to do in this assignment, and so it says the remaining part of the assignment involves doing the 2 experiments on each type of lever. The data are at this link, so let's unpack that statement. So here's the data. We'll come back to that. Okay, right here I say the remaining part of this assignment involves doing 2 experiments on each type of lever. The reason I say that is if you go to this part here, you'll find that the first class lever has 3 different measurements, and then the second and third class each have 2. We've already done 1 in the last assignment, so going forward, and I believe that starts at problem 12, is the second version of the first class lever. So you'll do 2, and then you'll do 2 on the second, 2 on the third. So that's what I mean by 6 more. Well, 2 experiments of each type of levers for a total of 6. Each time you do one of the remaining 6 experiments, you will have a calculation to do, as directed on MYPLTW. Clearly and legibly do those calculations. How about and answer any questions? Then you're going to scan or photograph that stuff and turn it in right here, as described here. So let's go through and let's just do one, sort of. So here we are. We're going to start at 12. It says, consider the following images of another first-class lever lifting a 1 kilogram mass, example B. So there it is. And we can zoom, oh my goodness, zoom up, zoom way up. The resolution on these cameras is amazing. I don't think it's really, you get really anything out of zooming up. Anyway, bottom line here is that we've got an effort force being applied by this force sensor, which is going to create a data graph, lifting this 1 kilogram mass with a great big moment arm. So you can imagine that the mechanical advantage here is not equal to 1 as it was in the first example. And so we'll have to find out what that is. And again, here's a picture of it in on shape. It'd be kind of fun to make that in on shape. Maybe we'll do that. And then it's got some discussion about how do you think. Thinking about thinking, that's what metacognitive strategy is, so you can kind of check that out. Then it says to explore the motion of the first class lever example B, open the simulation. So we're going to open it just as we did before, and here it comes, courtesy of Onshape. And you can, there we go. So there's that lever. If I click the right here, you can kind of see that it's when we put our force sensor here and apply the effort force, it's going to, we're going to have a value different than we did before. All right, so let's go back here, and then we want to view the video. So this is how the data is collected. That little thing the guy's holding is spitting out data wirelessly in newtons, the number of forces it's being pulled up with. And so that's the data file we're going to use. Let's see if it jives with our equations. All right, calculate the ideal mechanical advantage of the lever. Refer to the information in steps 12 through 14. Use your PLTW engineering notebook to show your calculations and explain your reasoning. Well, we're not going to do this. We're going to do this on a piece of paper. And why don't we do that right now? Let's see, what are they asking for? Calculate the ideal mechanical advantage of the lever. Well, if we want to do that, let's go ahead and write a few things down. There we go. So this is going to be, I'm going to write down, say number, I think it's 15, isn't it? 15. And this is the second run. A run means sort of an experiment. An experiment, you might do several runs to get large amounts of data, and then or do it slightly differently. Anyway, second run of first class lever. And it wants to know what the ideal mechanical advantage is. Well, we always know that it is a dimension associated with the effort force divided by a dimension associated with the resistance force. And the way we get that is we calculate that. No, we measure. And we do that here. So how can we do that? Well, we have this sinister measuring device here. What if I click here, there, and then there? That tells me that the distance in the y direction, so y is this way, back and forth, it's about 7.6 inches. So that'll be what? That'll be d sub r, right? Because this is a resistance force. So let's come back here, and maybe I can put this down here. I think I just measured that the d sub r, what is that? It's about 7.6 inches. Let's find out what d sub e is. Well, we can close this, and then we can go back. Let's get to a couple of escapes to get out of there. And we're going to measure from here. Well, let's do this. Actually, I may have made a mistake there. I probably want this to be level, don't I? I thought I could make this level. Let's do this. And let's lift this up. There we go. That's too much. Let's see if we can pull it back down. Doesn't look like it. Oh, let's go to isometric. Pull this guy down just a bit. Oh, right there. Now let's go to the right. Again, I'm trying to get this level so I don't have to, so I can just measure off the y value. I don't have to do any sort of calculations combining two different distances. Why won't this let me move? Oh, there we go. Okay. A little bit of lagging. Oh, there we go. Perfect. Okay. So I think that this one may be not quite right. Let's check that. This might be a little longer. So let's click the distance here. How about from, let's see. I can't really tell where it's. I'm going to do it from the center of here, of this post. There to there. 7 point, see how x is so small? Let's do 7.8 inches. So we're going to come over here and change that to 7.8 inches. Now for d sub e, let's do this. From here, we're going to click there, and then we're going to click, I think it hangs from the very end right there, and we get a y of 11, what? Oh, it took the distance all the way from there. I don't want that. So this tool is a little flaky. So I click there, and then I click right there, and I get 2.9. But x is almost an inch in this direction. You know, I think it might be easier to do something else. What if we just count squares? 1, 2, 3, 4, 5, 6, 7, 8. 8 squares for d sub e. 8 squares. So this would be some number of inches here, but I don't like that measuring tool. So we're going to say 8 squares. Let's mark that out, and let's measure from here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 squares. That's kind of suggestive. So that's 16 squares. And the reason we can do squares is because we're just taking a ratio. So I'm going to get effort is 8 squares divided by 16 squares. IMA is equal to 1/2. All right. Let's come back here. So we did number 15. Okay, calculate the ideal effort force needed to overcome the known resistance force. Okay, so 16. Let's see what that says. Calculate the ideal effort force needed to overcome the known resistance force. Okay, so I think that's what that's asking, is that we know that if we exclude friction, the effort force is going to be the ideal mechanical advantage times the resistance force. Is that right? That is not correct. Let's go back to the definition of IMA. That's F sub R over F sub E. IMA, oops, you can't see that, sorry. Let me move this up. IMA we know is F sub R over F sub E. Therefore, F sub E is equal to F sub R over IMA. Okay? So let's go back and ask and make sure that we understand what's going on here. So calculate the ideal effort force needed to overcome the known resistance force. Okay, the resistance force, what is this? This is equal to the mass times g, acceleration over IMA. So let's go ahead and calculate this. So that's equal to 1 kilogram times 9.8 meters per second squared divided by 1/2. So that equals, what does that equal? That equals 2 times 9.8. So that's going to be 19.6 newtons F sub E. As we come down here, this is IMA. Okay, and then the next one, what is that? Now let's come down a little bit. 17. All right, for 17, if we were in the lab, we would see this on the screen, and wonderful. Okay, but we're going to use the data file. So again, if you click on this link right here to get the data file, you'll get this graph. It says first class lever run 2, step 17. So if you come back here, you'll see that, yeah, this is step 17. So this is our data file right here. They want us to take the max value, and it looks like it takes us 24.2 newtons. Okay. 24.2 newtons, so let's write that down. So that would be F sub E measured is 24 point, what is that? 24.2. Alright, so I think I know what they're going to ask us. Okay, what's the actual mechanical advantage of the lever? Well, if we come back over here, whoops. What was that? That was number 18. 18 AMA is equal to F sub R over F sub E. And so the resistance we know is equal to 1 kilogram, which is, well, let me write it out, F sub E. And this is measured. So this is going to be 1 kilogram times 9.8 meters per second squared divided by 24.2 newtons. So that's 19.6 newtons over 24.2 newtons. And that number is equal to so I go to my calculator, 19.6 divided by 24.2, 0.81 AMA. Okay. Alright, so as we come down further, what's the efficiency of that lever? So the efficiency here, I think that was 19, is AMA over IMA, and the AMA is 0.81 The IMA is 0.5, and so we get an efficiency of more than 100%, so that's awkward. It's 0.162 times 100%, so we get 0.81 divided by 0.5 equals 1.62. So we get 162% efficiency, which is not really possible. It's due to some measurement error. So maybe I didn't measure these very accurately. With more time, maybe you can measure this thing a little better. But that's what we have. So let's go and, so for some of these, I've kind of cleaned these up, except for the last one. This one right here. This is just the data that's sitting there. So here's what I want you to do to this one. So you're gonna, I guess if I do it here though, you'll already have it. So that's okay. Grab it, double click this way, maybe come along, center it. Okay, then grab B and let's reduce the number of decimals. Whoops, too many. We don't need all those decimals. They're gonna get, they get bigger there. Now let's grab A and B, insert chart. And there it is. That's the chart we want to have. And we don't really need to do anything with it at this point, just have it there. And so that's what that graph looks like. Now, what they want to do, they want us to do is take the max value of force. And so equals max. Can I just grab it like that? I don't know. I may get angry. No, it took it. It excluded that one. 26.393, that looks to be about the highest. Okay, so that's the number we'd use for that. So I'm not sure why I got an efficiency greater than 100%. So on the second one, maybe one of you guys and gals can explain and educate me on why that's the case. But that's generally the way you want to do it. So as we come back here, you definitely don't want to do as I do. Rather, you want to do as I say. This is kind of a mess right here. So you want to do this much more cleanly and understandably. And with that, I will end this video.